Hi, my name is Calvin. This is Josh. We're from Team PASCAL, which stands for Pressure-Actuation Stimulated Chromodynamic Active Layer. So that's a mouthful of words, so we'll take you on a step-by-step journey through our process. So nature is beautiful and filled with color. But more interestingly, as such vibrant colors as seen on the wings of some butterflies or opals, they arise from nanostructures on the size of visible range. And this photonic structure, this nanoscale uniform array of nanostructures, is what gives this beauty. And so we want to take this to the depths of the swimming pool. So our goal is to bring a swimsuit that changes color upon applied pressure. So in order to meet these, our device has to meet certain criteria. One, it has to be capable of color change upon pressure, which the water will provide for us. As well, in order for repeated use or maybe iteration after a day, we need certain mechanical properties for us to satisfy being able to be used multiple times. As well, in order for us to enjoy the color change on the film, it has to have a large enough viewing area. It has to be water resistant, so it doesn't dissolve in the water. As well, flexible enough to wear on the arm, on the finger, or on your chest. As well, we've considered working temperature, response time, and as well, safe usage for our properties.
In order to meet the design requirements, we have elected to choose an elastomeric photonic crystal. A photonic crystal is essentially a material that has a periodic structure that interacts with the wavelengths of light. Specifically, our film uses Bragg scattering in order to actually reflect the light. So constructive interference will cause one particular wavelength to be reflected, while most of the rest will continue on through at a specific angle. Now, the elastomeric photonic crystal combines this with an elastomer. That is a flexible polymer, and this flexibility allows the photonic crystal to actually change its periodic structure with applied pressures. Now, why specifically the EPC is that it meets most of our design requirements almost right from the beginning. It is sensitive to pressure. It will change color upon a pressure application, as well as has tunable mechanical properties and tunable optical properties. It also has the tendency to be flexible and a sufficient area for our application. In addition, there's no external power required, and it is a much simpler device than trying to sense the pressure with a transducer, convert that to an electrical signal, then convert that back into a color from an LED or some other mechanism. In our case, it's just you apply the pressure, the structure changes, and you get a different color immediately. It's also fabricated of readily available and low-cost materials. The elastomer is basically a cross-linked methacrylate. In addition to this, however, the material must be able to be waterproof. And because of its pores, it can't be in direct contact with water, otherwise it will not collapse under the pressure. Thus, we need to actually seal the material in some sort of seal, such as low-density polyethylene, commonly known as saran wrap, to give an idea of how the material behaves. It's non-toxic, it's thin, it's flexible, as well as light, and most of all, it is waterproof, at least for our requirements. Before actually implementing this design, we decided to investigate it theoretically. First, to examine the optical properties, we just did a simple lumped model. We just assumed a simple 1D photonic crystal, so just the incident light and it reflects and the constructive interference. From this, the EPC should have a roughly yellow color. We also then did some lumped mechanical modeling. In this case, we tried to determine what would be a reasonable Young's modulus for the whole film. In addition, we examined whether our sealing material, LDPE, would rupture under the radii of curvature that would be relevant to our application. In this case, we found that LDPE is more than sufficient to survive the applications that the application that we have for it. In addition to lump modeling, in an attempt to increase the accuracy of our theory, we use finite element modeling using the software console. For the optical properties, we took the internal structure from published SEM images of the technology. Using that structure, from the finite element method modeling, we determined that before compression, the film should have a roughly green color. Notice that this is a bit different from the lump modeling, and I would view this as being due to the increased accuracy of the finite element modeling. However, it is still two-dimensional, so there still could be some caveats as to how well it actually models the material. While it's near its maximum compression, it should be approximately blue. For the mechanical properties, we applied stress to an array of unit cells, also with finite element modeling, and an array in order to balance between the computational requirements of the calculation and the actual accuracy. From this, we determined what would be a desirable Young's modulus for our elastomer in order to have the desired color change at the desired pressure. From this, and comparing to literature values, it resulted in a mole weight percent of cross-linking of our elastomer of about 0.58. However, for our system, this is an experimentally infeasible. The value is very, very low. So we elected to go with a cross-linking density of about approximately 10 mole percent as per the technology that was published to be working.
So the next steps, thank you. So the next step was to actually fabricate our device, and we've used a modified version of Dr. Arsenault's recipe. So it's comprised of three main steps. The first is to create a colloidal crystal film of silica nanoparticles. So by pure evaporation of silica nanoparticles around the size of 300 nanometers in a solution, our glass substrate sits, and as the solvent evaporates, the particles will conform to a close packed structure. Then the second step is to impregnate the actual CCF with polymer precursor and polymerize it via thermal initiation. And the last step is to etch and dry. So we etch away the glass nanoparticles with HF, and then we use freeze drying, and then we finally seal it with LDP for our water applications, underwater applications. So this is the performance of our initial results. So as you can see, we were able to achieve a film that could change color. We first wanted to use UV-vis spectrum to actually quantify the wavelength shift, but we could only, for this, our initial set of synthesis steps, we could only fabricate a film of limited size that was limiting for the UV-vis spectrum. So we've instead used hue, which is a quantitative description of what the human eye observes as color. And we've quantified a definite shift in the visible length. But we also came across further disadvantages from the previous method, which was we had small enough film, as well as brittleness due to thermal shock from freeze drying. As well, it wasn't a large area. We had some opacity in the actual film, so it wasn't a perfect colloidal crystal, but the silica nanoparticles themselves could not pack correctly. So that's why we've gone on to make some modifications to our synthesis. First, we fabricated CCFs, the silica nanoparticle structures, with restricted airflow. And so limited vibrations lessened the impact on the meniscus of the glass substrate sitting with the silica solution. And so it stabilized and gave us a more uniform CCF as well as better crystallinity. And because now these CCFs had better crystallinity, it was more dense. It was denser, and so the polymer precursor the hydrophobic polymer precursor could not go through the silica particles, so we allowed longer time to actually impregnate the particles. And finally, we've converted from freeze drying to N2 drying because we found that the brittleness of the film was not good for our application. So as you can see, it is a little difficult, but with the newer film, we get more iridescence, strong color, and a larger area film. So as you can see, so just for the CCF itself, the template of nanoparticles, you see with the the original design, the black curve, we see more amorphous scattering in the visible range. But with the newer red curve, as shown with the CCF, we can see a definite increase in the reflectance. And actually, yeah, as seen on the right here, you can see some opacity with the original design of our process with more amorphous scattering. But with the new CCF, it is redder. It is more of a pure color. And for our EPC, our photonic crystal, elastomeric photonic crystal, we do get scattering, but we've also had some improvements in terms of it closely matched the 550 as simulated on COMSOL. It was more green. As well, we could finally get a larger area film for the viewing area. So in terms of as up to our final modifications for our synthesis steps, we've achieved most of our design requirements to actually make an underwater device. And so it was safe, it was durable. After multiple compressions, we didn't notice any significant integrity changes or color changes. It was flexible. It could conform to a radius of curvature less than 0.25 centimeters. Viewing area was larger than a centimeter squared. It had a working temperature of more than room temperature. It could go down to 10 degrees Celsius as well. It did not dissolve in water. But our main, I guess our caveat was that it could not show reliable color change anymore.
Now, this begs the question as to, excuse me, as to why it does not actually exhibit a reliable color change. In order to determine this, we examine the different components of our product piece by piece. So first of all, we have our CCF, the colloidal crystal film, the assembled silicon nanoparticles. Now, we have shown that not only do we have good crystallinity, but we actually improved it. And because of the improved crystallinity, we have a significantly intense color, which should not be prohibitive of the actual color change. Now, the polymer is a very integral part of the film, being that it forms the majority of the film itself. And its mechanical properties directly impact as to whether the film is compressible. In our case, we use thermal initiation. This has the tendency to have a bit of an uneven polymerization because of differences in heat at different regions. Published technology has actually used UV initiation for this. We would have done that, but our limited resources prevented us from actually implementing UV polymerization system. So this difference could be one of the reasons for the lack of reliable color change. In addition, the cross-linking density may need to be readjusted in order to achieve the correct mechanical properties to have a color-changing film. The etching step, it's possible, now we etch with HF, which has the possibility of attacking the methacrylate polymer. However, we use dilute HF, only about 2%, and this amount is similar to occasions when PMMA, another methacrylate, is used as an HF mask for just quick etching with dilute HF. So we expect for our concentrations and times that it should not significantly damage the polymer film. In addition, it's possible that not all the silicon nanoparticles were actually dissolved out of the film, or that there were other deposits left behind. SEM images seem to indicate, however, that this is not the case. There may be small deposits, but at least nothing we can visibly see on SEM. In terms of our drying, there is a possibility that the surface tension of the water as it dries may tend to collapse the internal structure of the film, which is why we had elected to freeze dry the film. However, upon switching to nitrogen, not only do we still get a color, but SEM actually indicates that the internal structure of the film, which is these hexagonal shapes with the voids and the polymer in between, does not actually collapse upon itself. We still see the crystalline structure, indicating that surface tension should not be a major factor impacting the final performance. Having gone through all of this, the most likely culprit, I'll say, seems to be the actual polymer itself, given that this directly relates to the compressibility of the polymer, of the whole film. Another thing that we actually noticed from very recent results is the extent of wrinkling of the film has a large impact as to the reliability of achieving a color change. If the film is very wrinkled, it's very difficult to apply proper pressure, causing us to not see a color change. However, if it's flat, it's much easier to actually apply a pressure, and in those instances we have a higher, I'll say, success rate in different samples of actually achieving a visible color change. Now this wrinkling will go back to actually both the polymer in terms of its mechanical properties, as well as the step between etching and drying when we actually try to deposit the film onto a substrate, which will be the two areas of focus for anything in the future. Thus, our recommendations to try to achieve a working product for any of our work in the future on this is to use UV initiation to have a more even polymerization, to perform a cross-linking density series to try to adjust the mechanical properties. Also, because these changes were very amenable for us, achieving most of our customer requirements, we would recommend to continue to dry the film with nitrogen to fabricate the silica part nanoparticle array under controlled conditions where there is little airflow to disturb it, as well as to allow a longer monomer impregnation time to ensure we get a mechanically stable film. Now, in addition to these technical recommendations, there are also other applications for a film that would be useful to investigate. One is actually as an indicator as to whether a beer or pop would actually be flat. For when it would not be flat and desirable to drink, it has a high pressure. When it goes flat, the pressure actually drops, and our film should actually be able to detect this. In addition, there are applications in orthopedics and orthodontics. Also, there would be uses in tunable optical communication filters. But given these applications, our main goal is still, just as the transition from black and white television to color television revolutionized the television viewing experience, so do we want to revolutionize the underwater experience. Thank you. Anyone have any questions? Okay, any questions?
So when you do the array, you know the picture that you show, there are lots of defects. Is it because of particles or that, is it because of the particle that you have defects?
I would believe, yes, not a very good crystalline stacking. For that SEM image, it was actually a bit of a transition step between using just nitrogen and using the new air-controlled flow for the CCFs. So the newer CCFs actually have a much better crystalline stacking, which is at least partially visible in the SEM images, but we believe that those defects in the polymer are due to defects in the template, which is the CCF to begin with.
And one more. At the beginning, you said that you took the pictures from the paper, the reference, and then you did use a model in order to predict the wavelength that will be reflected, right?
Oh, with the FM modeling, yes.
Have you taken? Can you take now your pictures, you know, the size of your on film and the holes in your own film and plug it into your model and see how what you would expect and if it matches what you think?
Okay, I would say that would be very possible. It would also be useful to examine how our film, the shape of our film compared to those published SCM images to actually see how close our film might actually be to the published ones. But yeah, it would be very possible to take those values and plug them into the modeling to see how that would actually compare for our own film. We just have not done that yet. Any other questions?
Very nice work. Question is, have you examined the thickness of your particle film?
From SEM, the films that we did SEM on, they should be around 100 microns thick. However, depending on the we did various concentrations of silica nanoparticles, so we actually have different thicknesses of our CCF. So we will have films with different thicknesses depending on how we initially made the template. but we'd expect to be from around 100 to 300 microns in thickness.
From your study, what's the optimal thickness? Is thicker better or thinner better? Or something?
I think we definitely found thicker was better. That's why we've tried a range of concentrations with the silica particles we had. Thicker, wow, sorry. Excuse me. Thicker was definitely better because it could, so I think there were multiple benefits. So thickness also gives us mechanical stability. So it tends to wrinkle less, as well as we could get more larger area impact viewing area films out, because we could, oh, well, actually, we also used, in addition to that, we've used higher cross-linking density as well to give it more stability when we were etching away the silica nanoparticles. But also, thicker also gives us higher intensity of films out. So when we actually used a very low concentration, maybe like 1.5 volume weight percent, even less, actually 10 times diluted maybe, those ones were very thin, and only under the very strong glare under the fluorescent we could see color. But with these films, we could at least see, with normal fluorescence, we could see a high, strong intensity.
If you have a thicker film, it's more pronounced to crack.
Okay. Yeah, that
The
could
thicker
be a problem.
repeated the crack.
And that's why we've compensated. Yeah, I guess there is a compromise, but we've tried to compensate that for the reduced vibration in the oven, slow controlled controlled airflow, as well as not to disturb the meniscus as well. But there's also, I guess it's not, it doesn't fit with our application where we use silica nanoparticles, but other people, when they also make photonic crystals, colloidal photonic crystals, they could also use solvent that actually solubilizes the particles, and then that forms a continuous stacking along the way without any stacking, but it doesn't work with polymers, I guess, for us.